Good morning, class. I hope all of you are safe. This June first week has been very significant for us, right? Because on first we had the World Milk Day, right? On fifth we have the Environmental Day, and just 2 days back on seventh we had celebrated the World Food Safety Day, right? So I hope all of you are safe, stay home, eat healthy. Okay, so today in the course Physical Chemistry of Milk, we'll be looking at the colligative properties. Colligative properties, right? So most of you must have some idea about this in your school days, right? You must have studied about this colligative properties and all. Okay, so what are the colligative properties? Okay, so or what substance show these colligative properties? So before going to colligative properties, we will just look what is a dilute solution. So in the dilute solution, the amount of solute is very small in comparison to the amount of solvent, right? So the amount of solute that is dissolved in the solvent is very little or a minimum quantity. Okay, so this colligative properties is shown in the or dilute solutions exhibit these colligative properties. Okay, it is not shown by saturated solution or any other kind of solution. Only dilute solutions express these colligative properties. So the peculiarity of the colligative properties is that the properties of this dilute solution depends on the number of molecules. Okay, it just depends on the number of molecules that is uh, there in a given amount of solvent. Okay, and does not depend on the properties of the solute. Okay, so there can be different kinds of solutions. You can add different kinds of solutes in a solvent, but the colligative properties will depend on the number of molecules. Okay, only on the number of molecules, not on the properties of the solvent, not on the solute. Like the solute is very high molecular mass, or it is very corrosive, it doesn't depend on like properties like that. It just depends on the number of molecules in a given solvent. Okay, so there are certain conditions for a solution to exhibit these properties. So that is, as we had discussed, the solution should be very dilute. Okay, and the solute which we are adding should be non-volatile. അതായത് നമ്മൾ സോൾവെന്റിൽ നമ്മൾ ഈ സോല്യൂട്ട് മിക്സ് ചെയ്യുമ്പോൾ ആ സോല്യൂട്ട് വോളറ്റൈൽ ആയിരിക്കില്ല. അതായത് അത് ആവിയായി പോകരുത്, സബ്ലൈം ചെയ്ത് പോകരുത്, വേപ്പേഴ്സ് ആയി പോകരുത്. അതെപ്പോഴും ആ സൊല്യൂഷൻ്റെ അകത്ത് തന്നെ നിൽക്കണം. ഓക്കെ, then the third condition is that the solute does not dissociate or associate in the solution. അതായത് ആ സൊല്യൂട്ട് ഇപ്പം അത് ഡിസ്ഇൻറ്റിഗ്രേറ്റ് ചെയ്ത് പോവാണ്, അത് നശിച്ചു പോവാണ്, അല്ലെങ്കിൽ ആ സോൾവെൻ്റ് ആയിട്ട് റിയാക്ട് ചെയ്യുകയാണെങ്കിൽ നമുക്ക് ഈ പ്രോപ്പർട്ടീസ് കിട്ടില്ല. ഓക്കെ, സോ ഇപ്പോൾ നിങ്ങൾക്ക് എന്താണ് കോളിഗേറ്റീവ് പ്രോപ്പർട്ടീസ് എന്ന് മനസ്സിലായി അല്ലേ? എങ്ങനെയാണ് കോളിഗേറ്റീവ് പ്രോപ്പർട്ടീസ് വന്നതെന്ന് മനസ്സിലായി, എന്താ ഫാക്ടേഴ്സ് എന്ന് മനസ്സിലായി. അപ്പോൾ ഇതിനൊരു ക്വസ്റ്റ്യൻ ആണ് നിങ്ങൾക്ക്. സുക്രോസ്, NaCl, calcium chloride, these are three solutes. Okay, so I just want to know your opinion, okay, on which will be exhibiting the greater colligative properties. So just leave your answers in the comments. Okay, so in these three, sucrose, NaCl, calcium chloride, ഏതാണ് കൂടുതൽ ഇപ്പം നമ്മൾ ആ കുറച്ച് എമൗണ്ട് നമ്മുടെ സോൾവെൻറ്റിൽ ഡിസോൾവ് ചെയ്യുമ്പോൾ ഏതാണ് കൂടുതലായിട്ട് ഈ കോളിഗേറ്റീവ് പ്രോപ്പർട്ടീസ് ഷോ ചെയ്യുക? അതായത് ഇപ്പോൾ 1 gram സുക്രോസും 1 gram NaClഉം 1 gram കാൽസ്യം ക്ലോറൈഡ് നമ്മൾ 100 ml വാട്ടറിൽ മിക്സ് ചെയ്തു. സോ ഇൻ ദിസ് 3 സൊല്യൂഷൻ വിച്ച് വിൽ ബി ഷോയിങ് ദ ഹയസ്റ്റ് amount of this colligative properties. Okay, so now we understood what are colligative properties and which kinds of solutions show colligative properties. Okay, the conditions that are necessary for this exhibition of this colligative properties. So now moving on, we will be just looking at the 4 types of colligative properties. Okay, so as I had mentioned earlier, the properties depend on the number of solute particles present. Okay, and not on the identity of the solute particles. Okay, so as you can see in the image, there is the pure solvent and there is a solvent plus solute. Okay, so basically there are four types of colligative properties, that is vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Okay, so we'll be looking at these in detail in the coming slides. So these are the colligative properties. So before going on to that, we will just have a small discussion on the refractive index. So you must be knowing what is refractive index, right? So what is refractive index? Refractive index is the measure of bending of a ray of light when passing from one medium to another. So that is the basic definition of refractive index. So there are different ways we can define refractive index. Like we can define it as the ratio of sine of angle of incidence to the sine of angle of refraction, or we can define it as the velocity of light of a given wavelength in an empty space divided by its velocity in a substance. Okay, so these are the different ways in which we can define refractive index. Okay, so the refractive index of a substance, it varies with the temperature and wavelength of the light. So different wavelengths of light will be showing different kinds of or different values of refractive index, and the temperature of the refractive index will be also uh, temperature of the substance will also affect the refractive index of the substance. Okay, so the refractive index of water is around 1.33 0.299. Okay, so that is the refractive index of water, and for cow milk it ranges from 1.344 to 1.3485. Okay, so why is this variation? Okay, so the relation between solid contents and the refractive index is linear. It means as the solid contents increase, the refractive index will also increase. Okay, so as the concentration of the solution increases, the refractive index will also increase. And the fat does not contribute to the refractive index. In case of milk, as you know, milk is an emulsion. Okay, right? Fat, that is oil in water emulsion. So in case of milk, the fat does not contribute to the refractive index of milk. Okay, why is that? Because the light passes through the solution, right? The solution is the one, the component or the part that is playing the major role in the refractive index value, right? So now what is the significance of this refractive index? Why do we need to measure, or how will this property of refractive index help us? So you must be knowing, like, we are preparing a lot of food products, right? So in case of concentrating some kind of food, for example, we are making concentrated milk from normal skim milk. So how do we know when to stop, or how do we know that our product has reached its end point, or the maximum or the optimum properties? So for that we can use refractive index. We can set the value of refractive index. The unit of refractive index is usually measured in bricks. Okay, so in the image you can see that's a handheld refractometer. So in that refractometer, in that blue portion and the front of the refractive meter, there is a lid. Okay, so what you do is that you open the lid, you place a drop of the liquid, or for which you have to measure the refractive index, then close the lid, and facing the light, source of light, you measure the refractive index. Okay, so if you look at through that eyepiece, what you will see is that you will be seeing different type of graduations. Okay, so in that at the point where there is a difference in the color, you can see the upper portion of that reading is blue color and the lower portion is white color. So at the point where the differentiation or the demarcation occurs is the refractive index of that substance. So for this we can use this refractive index in the industrial, for as an industrial application for measuring the concentration. As a relation to the concentration, we can use refractive index. Okay, in case of this fruit juices, squash, jam, jelly, or etc., we are using this refractive index. If you look at the standards in FSSAI and all, it must be mentioned this much percent sugar must be there. In case of this sugar syrup of this rasgulla, this much bricks is needed. So in all that we will be using this refractive index. Okay, so then moving on to the next property, that is osmosis. So this you must have heard this term osmosis, right? So what is that? The molecules of a solvent passes from a solution of low concentration to a solution of high concentration. And how does this occur? It occurs through a semi-permeable membrane. So this osmosis, it occurs naturally in all around us, right? For the plants taking up water from the soil, nutrients from the soil, all of it occurs by the process of osmosis, right? So the what will happen is that when there is a higher concentration of solute, the solvent will move to that direction, right? So the solvent will move from a lower concentration of solute to that of a higher concentration. Okay, so that is what occurs in osmosis, and this happens through a semi-permeable membrane. Okay, so in the case of osmosis, we can divide the or we can classify the solutions into isotonic, hypertonic, or hypotonic. So in isotonic, what is the case is that on both sides of the membrane, the concentration of the solute and solvent is same. That is, there is no movement of solvent through the membrane. Okay, so both the sides, the concentration is same. In hypertonic, what is happening is that the concentration inside the membrane, or the part covering the membrane, is inside the membrane is having a higher concentration of solute. So what is happening is that the solvent will move from the other side to the inner portion. Okay, and in case of hypotonic, it is just the opposite. Okay, so inside the solvent concentration is more and it will move outside. Okay, so why is this important is that milk, as you know, is a mammillary secretion, right? So what is happening is that milk is always in an isotonic solution with that of blood. So both of them will have an equal osmotic pressure. Okay, so what is osmotic pressure? So osmotic pressure is the minimum pressure applied to a solution to stop the flow of solvent molecules through the semi-permeable membrane. That is, the molecule is passing through the membrane. Okay, so to prevent that, like we want to stop the flow, we are applying a force on the other side, right? So what will happen? Due to that pressure, the flow of the solvent is prevented. Okay, so that is the osmotic pressure. So the osmotic pressure can be given in formula as ICRT, where I stands for Pantoff index, C for molecular concentration of solute, R is the ideal gas constant, and T is the temperature in Kelvin. Okay, Kelvin units. Okay, so this is how we get the osmotic pressure. So now we've seen what is osmosis, then now we have understood what is osmotic pressure, right? So now we can see what is reverse osmosis. So as the name suggests, it is just the reverse of what is happening in osmosis. So in other words, we can define it as a membrane treatment process. Okay, it's primarily used to separate dissolved solutes from solvent. That is, we now know that we to stop the flow of liquids, we are applying this osmotic pressure, right? When we apply osmotic pressure, the flow of the solvent is stopped. Now what will happen if we increase that pressure? If we apply more pressure than the osmotic pressure, then what will happen is that the flow of the solvent will go in the reverse direction. That is, the solvent will move from a part of higher concentration to that of lower concentration. So what is happening is that it's happening the opposite of osmosis. Okay, so that is reverse osmosis. So you must have heard this RO, or reverse osmosis, everywhere, right? In our water filters, we are using reverse osmosis for desalination plants, that is converting salt water into fresh water. We are using this reverse osmosis. Okay, and you'll be learning in further classes, like there are different types of separation techniques that is based on this process. That is membrane filtration process, like nanofiltration, microfiltration, ultrafiltration. So these are membrane filtration processes which are based on this theory of osmosis and osmotic pressure. Okay, and another thing is that the osmotic pressure of milk, what contributes to the osmotic pressure of milk? So the osmotic pressure of milk is due to, as you know, it is a colligative property, right? So the dissolved dilute solutes will be the ones that are responsible. Okay, so what is the main contributors? The organic solvents and lactose. Okay, these are the major contributors to the osmotic pressure of milk. And there exists a complementary relationship between lactose and sodium chloride. That is, we know what we know that milk is isotonic with blood. Okay, so blood and milk has to maintain a constant osmotic pressure, right? So what will happen is that, for example, in the case of mastitis, okay, you must have heard the term mastitis. Okay, മലയാളത്തിൽ പറഞ്ഞ അകിടവീക്കം. What is happening is that the udder gets infected with various microorganisms, right? So what will happen is that the microorganisms cause different release different chemicals. They attack the lactose, they utilize the lactose, they produce acids and all. So what is happening is that the osmotic balance inside the udder is getting disturbed. Okay, so what will happen is that the body of the cow, in order to maintain the isotonicity, what will happen is that more sodium chloride will be pumped into the udder. Okay, so lactose is being depleted, right? Lactose എല്ലാം ഉപയോഗിച്ച് തീർക്കുകയാണ്, അല്ലെങ്കിൽ ലാക്ടോസ് ഡെഫിഷ്യൻ്റ് ആണ്. അപ്പോൾ ഓസ്മോട്ടിക് പ്രഷർ ബാലൻസ് ചെയ്യാൻ വേണ്ടിയിട്ട് ബ്ലഡിൽ നിന്ന് കൂടുതൽ സോഡിയം ക്ലോറൈഡ് മിൽക്കിലേക്ക് വരും. ഓക്കെ, സോ മോർ സോഡിയം ക്ലോറൈഡ് is coming into the milk, and that's why the mastitic milk, or the milk that is reaching to the end of the lactation, will be tasting salty. Okay, because in order to compensate the loss of lactose, the cow's body will be pumping more sodium chloride and salts into the milk. Okay, so that is what is osmosis, right? So now moving on, we can see what is the freezing point depression. Okay, so freezing point depression means a depression in the freezing point. Okay, so the law or the basis of this is that Raoult's law. Okay, so what does Raoult's law say? It says that the vapor pressure of a pure solvent decreases with the addition of solute. Okay, so it can be given as TF is equal to KFM, that is difference between the freezing points of solvent and the solution. KF stands for molar depression constant and M as the molar concentration of the solute. Okay, so 75 to 80% of the freezing point depression is due to lactose and soluble salts. We had seen earlier in case of osmosis also, lactose and soluble salts are the ones that is contributing to the colligative properties. Okay, so all the substance that is dissolved in the serum portion, okay, in the dissolved state in the milk, is the ones that are contributing to the freezing point depression. So the freezing point of authentic bovine milk, that is pure bovine milk without any adulteration, it ranges between 0.512 to 0.550 degrees Celsius. Okay, so it depends on the level of lactose and soluble salts, but the range is very narrow, right? There's very little range of freezing point values in milk. So where can we use this, right? We are studying the freezing point of milk, but what is the use of that? Okay, so the freezing point depression, as I said, is a function of osmotic pressure. Okay, so what will happen is that the addition of water in milk will cause a decrease in the freezing point. That is, if somebody is trying to adulterate milk with water, then what will happen is that the freezing point will decrease. Okay, and also the souring of milk, then what will happen? The lactose is broken down into lactic acid and all. Then again, the fortification of milk with lactose or SNF. Then further, what is happening? We are adding more salt and lactose into that milk, right? Then in that case, or we are adding sugar. Sugar is a form of adulteration also, like, right? If we add milk, sugar to raw milk, then it is also an adulteration, right? So all these things will increase the depression of freezing point. That is, the freezing point value will become lower and lower. That is, for example, if the freezing point of milk, suppose it is 0, right? It is not 0, it is like 0.550 and all, but assume that any freezing point of any product is you are considering it as 0, right? Then what we are doing is we are adding some amount of sugar. Then what will happen? It will go below. That is, the depression in freezing point will increase. that is it will go from 0 to minus values, right? So what will happen in milk, if you are adding sugar to a milk whose freezing point is already 0.55, then the value will depression will increase. That is, the value of freezing point on the new milk with added sugar will be maybe around minus 0.57 or something, right? The value will depression in freezing point value will increase. Okay, so where are we using this? In the image you can say it is an image of a cryoscope. That is, cryoscope is used to measure the freezing point of milk. So where can we use this? We can use this to check the adulteration of milk, right? For example, if someone is adding water, usually we are going for lactometer and all, but in this way, while freezing of by detecting the freezing point of milk, we can get very accurate values. Okay, if any addition of water or any other adulterants has been occurred or not, right? So cryoscope is used to measure the freezing point of milk, and it can be used to detect the addition of water in milk. Okay, so when what will happen if water is added, the concentration of lactose and salt will decrease, right? So if the freezing point of the milk was minus 0.55, then after adding water the value may change to maybe 0.51 or 50, like that. So the depression will decrease. Okay, so I hope you have understood the freezing point depression, right? Now moving on to the next colligative property, that is lowering of vapor pressure. So we had discussed this Rolle's law in the last slide, right? So Rolle's law is the mathematical description of vapor pressure lowering phenomenon. Okay, so the vapor pressure of the pure solvent new solution can be calculated as C solvent into PO, that is the vapor pressure of solution is equal to the vapor pressure of solute above the solution multiplied by the vapor pressure of the pure solvent. Okay, so what will happen is that, as you know, water it the process of evaporation continuously goes on, right, on the water surface. So when we add the solute, what is happening, that the surface area is reduced, right, because solute molecules are occurring some taking up some of the space over there, right? So what will happen is that the amount of water that is getting into the vapor state will reduce. Okay, so the liquid molecules at the surface of the liquid can escape into gaseous phase. Okay, when they have the sufficient amount of energy to break free of the liquid's intermolecular forces. You must be knowing that all the molecules are attracting to each other, right? So when a molecule gains enough energy, it will break away from the liquid state into the gaseous state. Okay, so what will this non-volatile solutes do? It will reduce the amount of surface area available for escaping of the solvent molecules. Okay, so what will happen is that the vapor pressure will decrease. Okay, so if this for qualitative properties, what we had said, an important factor was that the solute that we are adding should be non-volatile. Okay, if it's volatile, what will happen? It will also evaporate and it will also add to the vapor pressure, right? So if the solute has its own vapor pressure, then the vapor pressure of the solution may be greater than the vapor pressure of the solvent, right? That's what we said. So for colligative properties, always the solute must be non-volatile. Okay, so this is the lowering of vapor pressure, and based on this there are we one there is one more property that we must be looking into due to this lowering of vapor pressure, that is elevation in boiling point. Earlier we had seen what depression in freezing point. Now there is this elevation in boiling point, that is the boiling point of a solution will be greater than that of a pure solvent. Okay, so as you know, what is boiling point? Boiling point is the temperature at which the vapor pressure of liquid equals to the external pressure, that is atmospheric pressure under normal conditions. So when both the pressures are equal, then the liquid starts boiling, right? Vapor pressure, when both are equal, the liquid starts boiling. So what will this solute do? It will lower the vapor pressure, right? So what will happen? The solution will start boiling at a higher temperature. Okay, so when a non-volatile solute is added to solvent, the vapor pressure of resulting solution is lower than that of the pure solvent. Therefore, a greater amount of heat must be supplied to the solution for it to boil. So the boiling point of normal milk is 100.15 degrees Celsius. We know that for water it is 100 degrees Celsius, right, under normal atmospheric pressure. In milk, due to the lactose and other minerals and salts, the vapor pressure of milk is 100.15 degrees Celsius. That is, the boiling point of milk is higher than that of the pure water. Okay, so as we have seen in the case of freezing point of milk, the adulteration of milk with water will lower the temperature of will lower the boiling point of the milk. Okay, that is, when we add water, the milk will start boiling before it reaches 100.15 degrees Celsius. Okay, so this depression in freezing point we are using in many places, like for example, for keeping the fish and all fresh, we are adding some salt to the, or the fishermen are adding some salt to the ice, so that the depression in freezing point is greater. That is, the ice will stay cooler for longer time. Okay, in case of in milk, for making kulfi in the traditional way, what they are doing is that they are keeping the kulfi molds in ice. Okay, and they are adding some salt to the ice, so that the freezing point of the ice decreases. Okay, so the kulfi will also start freezing. Okay, so these are the some practical applications of these properties. So hope you have understood what we have studied. If any doubts are there, do feel free to contact me. Okay, thank you.